Hello everyone, Dr. Nat here. So we are doing lecture week 6 for electronic communication circuits. I just got back from my emergency. Now I'm recording, so hopefully you guys are watching this. Okay, moving on to the next page. Okay, so let's do a little recap on what FM and PM is and what's their difference. So here I have a carrier. I have my carrier over here. Okay, so this is my carrier. Oh no, I cannot remove it for some reason. Let's just delete that. So this is my carrier, okay, and this is my modulating signal. Now for FM and also for PM, we will have a center frequency. The center frequency is dependent on the carrier frequency. Now a center frequency, let me write that down. Center frequency is the midpoint to where it deviates to the maximum or to the minimum. So for example, if my deviation is 30 kilohertz and my frequency carrier is 1000, so let's say our center frequency or FC is 1000 kilohertz and my deviation frequency is plus minus 30 kilohertz, that would mean that my maximum frequency for my FM signal would be 1030 kilohertz and the minimum would be 970 kilohertz, right? So I have my center frequency or my carrier frequency, that is the default frequency. If there is no modulating signal, that is going to be my default frequency. The carrier frequency is the default frequency for both FM and as well as PM. Okay, great. And then the frequency deviation tells us how far the frequency can shift. So the positive will be the maximum and negative will be the minimum. And that is why FC is called the center frequency or the midpoint frequency for an FM as well as a PM. Okay, so now let's take a look at this diagram. For some reason, I can't get rid of these things. How do I do this? Okay, so we are going to talk about FM as well as PM. So here, let's take a look at this guy. This guy is increasing. So increasing and then it reaches a peak. So that is the maximum value or the maximum amplitude for the modulating signal. And then it goes down and then it reaches a throw, and that is going to be the lowest amplitude, right? Okay, so this is max amplitude and this is minimum amplitude. Now FM, why is it important to know the amplitude? Because FM is a function of amplitude, and because of that its frequency will be dependent on the amplitude. So the higher the amplitude, the higher the frequency, and the lower the amplitude, the lower the frequency. So let's take a look as to how this is. I know I've covered this in class. This is just a recap. Bear with me. If you know this already, you can skip. So we are increasing. That means my frequency will start to increase. My frequency will be increasing. Let me use arrows instead of writing that. So my frequency will be increasing. At this point, it says that there is no signal. Remember what I told you? If there is no signal, it will go back to the mid frequency or to the defaulted frequency. And that would be the frequency carrier. So at this point, where there's no modulating signal, your frequency for your FM signal will be just FC. So when it increases in amplitude, this guy also increases, and at the maximum amplitude, this is the highest point to where this is the highest frequency the FM signal can attain, and then it decreases in amplitude. Therefore, you know that it would be stretching. So I'm going to put left side arrow to indicate decreasing. Okay, and then we are increasing again. This is our minimum point, which means that at this point this is going to be our lowest and highest over here, and then it's increasing, which means that it is going to be faster in frequency, and then again we find the peak, whereby we have the maximum amplitude for the modulating signal, and therefore we will also have the highest frequency at this point. Now again, when there is no modulating signal, therefore this guy will go back to its midpoint. It will not deviate by a max. It will not deviate higher, or it will not deviate slower, but it will stay at FC. Now when we were talking about FC as well as FD, the maximum would be FC plus FD, the deviation frequency, while minimum would be FC minus FD. And I told you just now in my example, it was 130 kilohertz, sorry, 1030 kilohertz, and the minimum was 970 kilohertz. So you can already, figure this out, that at the maximum point, it's going to be at the most maximum. This is going to be 100 because this is the carrier frequency, and this is going to be where we get the highest. So that is going to be our 1300 kilohertz. Now to get from 1000 to 1030, it will start to increase slowly, and this part is where it starts to increase slowly. So this whole region is going to be increasing slowly in frequency, and up to a point where it is corresponding to the maximum amplitude, you will get 1030. Now when it is at the lowest, you will get what did we calculate just now? 970 kilohertz. So again, from 1030, it will start to move slower and slower and slower until it reaches 970 kilohertz. Okay, so I hope that makes sense to everyone. So let's talk about FPM if we already understand what FM is. Let me get rid of the drawings first. Again, okay, so let's talk about PM now. So PM, what does PM mean? PM is phase modulation. It is a function of the rate of change. So here, if I'm looking at my modulating signal, when it is increasing, my dx dy is, or my rate of change is positive. And at this point, at the maximum, it's a constant, therefore my dx dy is going to be 0. And then when it's going down, it's a negative slope, right? So it's dx dy is going to be negative, and then going up, this is going to be 0, and then going up, it is going to be positive, and at this maximum point, it's going to give me a dx dy of 0, a rate of change that is the rate of change of a constant is 0, and then this slope going down will give me a negative. This slope going up is going to give me a positive, and this guy is going to give me a 0. So how does this look like for the PM? So for a positive slope, my frequency will be increasing, and then at the 0 point, it will go back to being FC. And then going down, it will start to stretch, or it starts to decrease. And then at the 0 point, it's going to be FC again. And then it's going to be increasing. So it's going to be increasing in frequency as well. Okay, and then we have our 0, which means that it's going to be FC again. And then it's going to be negative. So it's going to stretch, and so on. So my question is, where does the maximum and minimum frequency occur, like FM, right? So here, the maximum occurs at the 0 crossing. So we have our slope. So this is going to be our lowest frequency possible. So this is going to be the lowest frequency possible for the PM signal. And at this point, the 0 crossing, for a positive slope, this is going to be the highest frequency for your PM signal. And then again, this is going to give you a lowest frequency, and at this point, it's going to give you the highest frequency. Okay, so that is the difference between FM and also PM. FM is very dependent on amplitude. The higher your amplitude of your modulating signal, the higher your frequency. And vice versa. But for PM, if it is constant, you will go back to the mid frequency or your FC. If it is a maximum, you will add it with FD, that is going to be your frequency. If it is a minimum, you are going to minus it with FD. Your frequency will always range between these two values, and the midpoint is going to be FC. Okay, so FC, FC plus FD, and this is FC minus FD. So that is the range of frequencies that the PM signal or the FM signal will move around or will have. Okay. Okay, so this is an example that I've told you before. Let's just recap on it. So assume a frequency of 150 megahertz. If the peak amplitude of the modulating signal, so it's talking about peak of the modulating signal, causes a maximum frequency shift, which means that this is going to be your positive FD or plus minus. So this is going to give you 30 kilohertz. Therefore, you already know that your FD is plus minus 30 kilohertz because this is the maximum, and the maximum will always have a minimum. So that's your maximum and minimum. Therefore, the total frequency deviation is 150.03 because 1000 megahertz plus with 0.03 will give you the maximum, and then 100 minus 0.03 will give you the minimum. And it's saying that the difference between these two guys is equal to 60 kilohertz. But the way that we would write it is plus minus 30 kilohertz. So whenever they ask you what is the FD, what is the maximum frequency deviation, you would write it as plus minus 30 kilohertz. Okay. So again, let's just try to make sense of this so that we are comfortable working with FM and PM. So at this point, I assume you already know what's going to happen. So when we are increasing in amplitude, the FM will also increase. At this point, there's no signal. This is going to be FC. This is going to be FC. So at T1, the modulating signal is increasing. Therefore, our FM also increases. Our PM also increases. At the zero crossing, you will get the highest frequency. And then when your modulating signal is constant, this is at T2, you will get for FM, since this is a constant at the highest amplitude, therefore you will get the highest frequency for FM. But for your PM, you will revert back to your mid frequency, which is FC. And then going down, your FM will stretch out, or the frequency will go slower. But for your PM, at the zero crossing, you will get the lowest possible frequency. So let's take a look if that is the case. Yes, this is the biggest or the slowest. And then at this constant, lowest constant, you will get the biggest stretch or the lowest frequency for FM. But for PM, you will just revert back to FC. Okay, so hopefully at this point it seems a little bit clearer. So you can go through the table yourself and see if it makes sense and if it is you understand it. If not, please see me in class. Okay, so again, the difference between these two guys, these two modulation, one is dependent on the rate of change, the other is dependent on the amplitude. So note that FM wave, the maximum deviation occurs at peak positive and negative amplitude of the modulating voltage. However, the phase for phase modulation, the maximum frequency occurs at exactly the zero crossing points, either for the positive slope or the negative slope. Now I'm going to show you the relationship between the modulating signal and the carrier deviation. So here we have a modulating signal amplitude that is increasing. We know that FM as well as PM is dependent on the amplitude as long as it's not constant. So since this is increasing, the frequency deviation will also increase for PM and also FM. However, if the signal frequency of FM is increasing, the only modulation that is affected is going to be PM. FM is not affected by FM. FM is only affected by amplitude. So only PM is affected by FM. So here is an example of a frequency modulation. Here, instead of increasing or decreasing in frequency, we will see phase reversal or a phase shift of 180 degrees. Hence the name phase shift keying. We will see a 180 degrees phase shift whenever we see this guy. Whenever the signal changes from 0 to 1 or 1 to 0. So the phase shift keying doesn't tell you exactly when 1 or 0 happens. So you have to keep track of it, because 1 and 0 looks exactly the same. So here is 1, this is 0. The way that it looks is exactly the same, but it only detects this change. So it's only dependent on the change of the signal. So only the change. If it is constant, it goes back to the frequency carrier. So again, it behaves like phase modulation because it is dependent on the rate of change. When there is a change, then you would get the phase reversal. So when a binary voltage level occurs, the modulator, which is a phase shifter, changes the phase of the carrier, not its frequency. So with this change, it changes the phase, but it doesn't change the frequency. Here, the phase shift that is used is 180. Therefore, you would see the phase reversal. But other values can also be used. So we have seen phase reversal happening before, which is in DSB-SC for AM. Right? Double sideband suppressed carrier. When the carrier is suppressed, you would see this pinched look. Remember? You would see this pinched look. This is your DSB-SC, and this is how your modulating signal would look like. It follows, but there is a phase reversal. So this phase reversal is at the middle. Okay, so phase reversal is always looks like a pinched. Okay, so moving on. So now we are going to talk about FM sidebands. So before I talk about FM sidebands, I want to remind you how AM sidebands look like. We talked about AM signal, and this is how it looks like. Oh, sorry about that. So this is going to be our carrier. Whoops. Let me try this again. Okay. Again, AM signal. We have our sidebands, USB, LSB, and this is going to be our frequency carrier, and this is our AM signal. This is a perfect AM signal without harmonics, without any noise. So this is how it looks like. But for FM, we see that we have a lot of sidebands that we need to think about. It will give you a headache, but that's okay. This is part of the learning process. FM will have more sidebands than AM, and that is common. So here I start with FC, similar to AM. Then I have FC plus FM. I have FC plus 2FM, FC plus 3FM, FC plus 4FM. And how do we actually denote these sidebands? We will call them as the first sideband, the second sideband, the third sideband, and so on. Okay, so this is how we would call it. This is the common way of seeing it, and this is just the carrier. Okay, so why do we have all these sidebands? These sidebands actually when we add up all of these waveforms, or all of these waves, you know that each sideband is a wave on its own, but when we add them together, they form our FM. So the reason why we are able to get a fixed amplitude is because when we sum all of these things, or all of these components together, they actually add up to give us a constant amplitude. So keep in mind that FM signal has a constant amplitude in the time domain. So this is what we mean by constant amplitude. Remember, AM looks like a tamarind. It does not have a constant amplitude. This is what it looks like. This guy is flat, top and bottom. So very different. This is AM, okay? Since an FM signal is a summation of the sideband frequencies, the sideband amplitudes must vary. They must vary so that when they add up together, they can form the fixed amplitude. The only thing that is varied is going to be the frequency. The sideband's amplitude must vary with frequency deviation and modulating frequency. The sum of sidebands is to produce a constant amplitude but variable frequency. Since many frequencies are at play, theoretically, the FM process produces an infinite number of USBs, upper sidebands, and lower sidebands. Therefore, theoretically, you would have an infinite bandwidth, which is not good. Typically, any sideband whose amplitude is less than 1% of the unmodulated carrier is considered insignificant. So if this guy is like 1 dot and this dot is less than 0.01 times the carrier, therefore we can ignore it. But if it is more than 1% of whatever the carrier is, we have to acknowledge it and allocate bandwidth so that the signal, FM signal, is not distorted. Okay? So as with AM, we had the modulation index. We also have modulation index for FM. So modulation index for FM is given by this equation. MF equals to FD over FM. Where is FC? It's not part of the equation. So in this equation, you are talking about deviation, frequency deviation, and modulating frequency only. So it's different. Remember, for AM, we were talking about VM over VC, the ratio of the modulating versus the ratio over the carrier voltage. But for modulation index for FM signal, it is talking about frequency deviation over the modulating frequency. Okay, for example, if the maximum frequency deviation of the carrier, so we know immediately we know that this is FD, and the maximum modulating frequency is 2.5 kilohertz. Therefore, FD is 12 and FM is 2.5. This would give me 4.8. So in most communication systems using FM, maximum limits are put on both the frequency deviation and the modulating frequency. So in standard FM broadcasting, the maximum permitted FD is 75 and the maximum FM is 15 kilohertz. Therefore, this would give us a maximum modulation index of 5. Anything beyond that would be the commission will not support this type of signal, meaning to say it's illegal. Okay, so this is known as deviation ratio. So again, modulation index, the other name for it is deviation ratio. This is not the same as frequency deviation. This guy is MF. Frequency deviation is frequency, not FD over FM. Okay, deviation ratio versus frequency deviation is different. Okay, so we have an example. I believe this example is not complete, my bad. So I'm gonna add another info here. So our carrier is going to be this guy. Okay, so given a carrier frequency of 1000 kilohertz, what is the deviation ratio if the maximum deviation is 25 kilohertz? This is FD. and the maximum modulating frequency is 7 kHz. So I can find out the deviation ratio, whereby it is given by FD over FM, and FD is 25 kHz over our FM, which is 7 kHz. That is going to give me, I don't know, my brain is not a calculator, but it could be 25 divided by 7. So we are going to get 3.57. So kilohertz is cancelled out, so I don't have to care about that. So my modulation index or my deviation ratio is going to be 3.57. So now the next question is, what is the maximum frequency and minimum frequency of this FM signal? So maximum frequency, not maximum deviation. Maximum frequency, maximum frequency is just what is the largest frequency that it's going to have. So that would be FC plus minus FD. So this will give us our maximum and minimum frequency. FC plus FD, and minimum will be FC minus FD. So FC is 1000, FD is going to be 25. This guy is going to be like that. So that is your answer. 900, so 975 kilohertz. Okay. Okay, let me erase this first. So remember that I told you FM sidebands are a lot, like a lot, and if it will expand, I mean the sidebands will go all the way up until infinity bandwidth unless we put a limit to it. And the limit that we are putting it is based on Bessel function. Bessel function tells us which sidebands are significant enough to be considered so that we can allocate appropriate bandwidth. Again, Bessel function tells us what sidebands are significant enough so that we allocate enough or sufficient bandwidth so that our signal is intelligible, or our signal is not distorted. So Bessel function is described using this FM signal equation. This FM signal equation, this is VFM, instantaneous value of the FM signal. We have seen this before for AM, whereby the AM signal changes with time. Same case over here, the instantaneous value will change with time. So it is a function of time. And here we have our peak value, or our peak amplitude of the unmodulated carrier. And we have our sine wave here, sine 2 pi fct, and this is new. For AM, we didn't have this plus thing. For FM, we do have it. This is our phase. So if I were to simplify this in a more common way, I can write it like this. It is more, it looks more common this way anyway. So omega ct plus theta. And theta is the phase. Okay, so the term, this term is the phase angle of the carrier. The phase angle of the carrier. This equation is solved with a complex mathematical process known as Bessel functions. The derivation and solution is not covered in this class, but we will go through the equation to make you understand intuitively how to use it. Okay, so the Bessel function, which is this guy, this equation, my face is covering part of it, but that's okay. This equation gives us J. Now what is J? J is the carrier or the sidebands. Now depending on the number n, if n is 0, it tells us the value of the carrier. If n is 1, it tells us the value of the sideband, first sideband. If n is 2, it tells us the value of the second sideband. Now the values is dependent, the values of the sidebands is dependent on the modulation index. So this is a plot of the Bessel function data. The x-axis is modulation index and the y-axis is the value of j. The value of j tells us the amplitude of the sideband or the carrier. And n tells us, again, n tells us the number of sidebands or the carrier. So if n is 0, it tells us the carrier amplitude. So if my modulation index MF is equal to 1, therefore the place that it intersects, let me try to map this like so. So J0 intersects with MF equals to 1 at this point, and this point is at value 0.77. Therefore, if I were to plot this, my carrier would have an amplitude of 0.77 given by J0 or J0. And then for modulation index 1, my sidebands would be, this is going to be my first sideband J1, and J1 intersects with MF1 at this point, which is 0.44. Therefore, my first sideband given by J1 is going to have an amplitude of 0.44. So this is FC plus FM, FC minus FM. This is my first sideband. And then my second sideband. So the second sideband is going to be given by J2. And J2 intersects with MF2 at this point. Sorry, MF equals to 1 at this point. And this point is 0.11. Therefore, my second sideband, I'm going to make this further a bit because I don't have space to write down there. So this is going to be my second sideband, 0.11, 0.11. And this is FC plus 2FM, second sideband. First sideband, second sideband. Okay, and again we look at the third sideband. The third sideband is J3 and it intersects with our MF equals to 1, and the value is somewhat 0.02. Now 0.02 is still above 1%, so we are going to consider it to be part of the bandwidth. So 0.02, this is going to be FC plus 3FM. Same case over here. I am so sorry for this very beautiful drawing. So please don't do this in your exam. Draw nicely. I don't have a ruler here. Okay, so do we have to use that diagram? No, not necessarily, but you need to understand how to use it. Typically, you would get this table. This table summarizes the values of the sidebands, the carrier, and also the sidebands for each modulation index. Great news, right? So we saw that modulation index 1 gave us a carrier amplitude of 0.77. The first sideband was 0.44. The second sideband was 0.11. The third sideband was 0.02. Now, anything that is lower than 1% is not going to be counted as part of the bandwidth, and therefore there is no value allocated for the other sidebands. But you can see that the further down you go for the modulation index, the more sidebands you will have. Okay? Alright. Okay, so there is a note here. Note that some carrier and sideband amplitudes have negative signs, which means that the signal represented by the amplitude is shifted in phase by 180 degrees. So if I were to draw this, previously, okay, let's use an example. Oh, this is too much. Let's use this guy, okay, 2.5. So hopefully I can draw this nicely. Not too confident. Okay, so straight line. We are talking about MF equals to 2.5, whereby it has a negative value. So how does that look like? The negative value is specifically for its carrier. So that would be my midpoint. Oops, sorry. it says a negative value. Therefore, it starts here, but it's going down instead of up. So this value would be minus 0.05, and this would be your carrier. So 0.05 is actually small, right? So I need to make this shorter. Minus 0.05, like that. And then for your first sideband, this is going to be FC. For your first sideband, which is FC plus FM, this is positive 0.5. And this is positive 0.5. This is FC plus FM, your first sideband. And then your second sideband is going to be over here. It's going to be 0.45, slightly lower but not too low. So this is FC plus 2FM. So you know the drill. Same case over here. It needs to be in pairs. So FC plus 2FM. Sorry, this is not plus. This is minus. Minus. Let me rewrite this. Okay. Oopsie. This is FC minus FM. This is FC plus FM. FC plus 2FM. FC minus 2FM. Okay, so on the other side, it's supposed to be minus. Remember, it's a lower sideband. Okie dokie, next. So let's take a look at this diagram. It has our frequency, FM signal in the frequency domain. We have modulation index of 0. We have index modulation of 1 for this guy. And this is 2, and this is 0.25. So for 0 modulation, it means that you're not transmitting any signal. Therefore, you would not have any FM, right? So if you don't have any FM, what is there to put here? Nothing. So you will only have FC. So if you are only transmitting FC, therefore all your power will be concentrated to transmitting the carrier. Therefore, this is why the carrier has an amplitude of 1.0, 1 or 100%. Okay, and then for modulation index of 1, you can see that this is what we drew earlier. Okay, so nothing new here, same, it's the same. And then for modulation index 2, here it is 0.22. So now your carrier is smaller. When you are going further down the modulation index, your carrier becomes smaller and your sideband becomes bigger than your carrier, which is not what we've seen before for AM, right? So but FM, that is the case. So here we have 0.58 for the first sideband, 0.35 for the second sideband, and then 0.13 for the third sideband, and 0.03 for the fourth sideband. So again, anything that is below 0.01 is not going to be part of the bandwidth. Okay, so last example over here, 0.25 modulation index, kind of looks like AM, not AM, it is still an FM signal. So this FM signal is very narrow. It is called narrowband FM. Surprise! So this is modulation index 0.25, carrier is 0.98, first sideband is 0.12, very small, which means that your priority for your power is given to FC instead of FM. So what does that give you? Let's talk about it. So your narrowband FM given by modulation index of 0.25 prioritizes your carrier instead of your FM, which means that if your modulating signal is in your FM, your output would have a low signal to noise ratio. Because why? Because your signal comes from FM. If your signal is low, it means that it's not going to have a high SNR. That's just how it is. So low signal, low SNR, high signal, high SNR. But if the noise is super high, then your SNR can be low as well. But there's no case where your signal is low that your SNR is high. It doesn't work that way. So low signal, low SNR. Okay, and high signal can be high SNR, can be low SNR. If high SNR if your noise is low, low SNR if your noise is high. Okay, so just it's just math. All right. Narrowband FM is used to conserve spectrum space. We've seen it. It looks like a triangle. Obviously, it's going to conserve space. It's not occupying much compared to the other modulation index that has a bazillion sidebands. This guy only has 2, looks like a triangle, very efficient in terms of spectrum, but very bad in terms of SNR. Okay, so not really great. But if you need small spectrum, then yes, narrowband FM is the way to go. If you need high SNR, then narrowband FM is not the one that you would go for. Okay, it is widely used in radio communication. So in your radio communication, you have all these radio stations and they actually look like this. So let's say my favorite would be, no, I don't have a favorite. So let's talk about hits.fm. The frequency is, I believe, 92.5. Is it kilohertz or megahertz? I don't remember. But this triangle tells us that any deviation within this triangle, it is still going to respond to hits.fm. But once it goes out of the triangle, it's going to go to Surya or something, other radio stations. So this is how it works. Okay. Alright, so 40 minutes. I'm going to go for another 10 minutes and then I'm going to cut this video to become part 1. Okay, so bear with me. So FM bandwidth with Bessel function. So I told you when we have when we have high modulation index, we're going to see more sidebands, and that's going to give us a bigger bandwidth. That's not it. We have to allocate a bigger bandwidth for the FM signal to be transmitted properly. So how do we calculate that? So how do we calculate the bandwidth without using the table? Because the table is like a lot. So we have a formula for that. So this is our formula using the Bessel function. So the bandwidth can be calculated using this equation, whereby it is 2 times FM times N. What is N? N refers to number of sidebands. So, for example, we were talking about MF equals to 0.5, whereby it looks like that. It only has one sideband, right? This is your FC, this is your first sideband. Therefore, it only has N equals to 1. So, if I were to find out the bandwidth, if my modulating frequency is 1000 kilohertz, therefore, the bandwidth that I need to produce this narrowband FM without any distortion would be 2 times 1000 kilohertz times with N equals to 1. So I'm just going to write 1 instead of writing it like that. So the bandwidth that I need is 2000 kilohertz for my radio station to be able to be transmitted properly, or the bandwidth that I need for my radio station to work properly. Okay. So this is another example. FM bandwidth with Bessel function. Assume that the highest modulating frequency to be 3 kilohertz. So that is going to be your FM. And the maximum deviation is 6. So this is your FD. So MF, we can calculate MF, modulation index or deviation ratio, using FD over FM equation. And this is going to be 6 divided by 3. You're going to get 2. Okay, so in your table, you would refer to this table. Modulation index of 2 would give us a N equals to 4. Therefore, your bandwidth is going to be 2 times FM is 3 kilohertz and your N is 4. So 8 times 3 is what? 24 kilohertz. That is your answer for this question. So apart from using the table or using the Bessel function to find out the appropriate bandwidth for your signals to be working or to be transmitted properly, we have another formula to find out bandwidth, and it's called the Carson rule. So the Carson rule is given by bandwidth is equal to 2 times deviation frequency, maximum deviation frequency, plus with maximum modulating frequency. So if we are able to find out MF using FD over FM, we are going to be able to plug in these numbers as well. So assume the highest modulating frequency to be 3, maximum deviation to be 6. You would add this together, so it's going to be 6 plus 3, that's 9, and that's going to give you 18 kilohertz of bandwidth. Now, if we were to compare Bessel bandwidth with Carson bandwidth, previously this is the same values, but for Bessel function we got the answer as 24 kilohertz, but for Carson we got the answer as 18 kilohertz. The difference is that Bessel takes note of anything that is greater than 1% of the VC, of the carrier amplitude, but for Carson it only cares up until 2%. Anything that is less than 2% is going to be ignored. Therefore, if you ignore more sidebands, you would have smaller bandwidth. So that is why Carson has a smaller bandwidth than Bessel. Okay, so I'm going to end it here. This is going to be part 1. Stay tuned for part 2. Okay, bye for now.